Okay. Welcome to problem solving session for week 11. Today we are going to discuss few questions based on test hypothesis. So before that I will quickly go through the main formulas that we will need to solve the problems. Or maybe with the questions we will discuss those formulas. Okay. So this So first question is, suppose we want to test whether or not girls on average score higher than 600 on their SAT verbal section. The standard deviation for this data is given is 100 and alpha is given to be 0.05 and the random sample of 20 girls is taken, which is given in this is the data for 20 girls. Now the test hypothesis is, null hypothesis is mu is less than equal to 600 and alternative hypothesis is that mu is greater than 600. So we need to test this hypothesis. So this H naught is mu less than equal to 600 and H1 is mu greater than 600. So as it is less than equal to, so we will use this one tail test, okay, and this sigma for sigma for whole population is given, which is 100, alpha is 0.05. So we have this data and we need to test this hypothesis, right? So now we will use this test those. So in hypothesis testing, we will first we will have some test statistics. We will calculate a test statistics. Calculate a test statistics based on given data and level of significance. Not significance level is used, will be later. Then what will we do? We will find the critical region with given alpha, which is our level of significance, and then we will compare these two quantities to check whether our null hypothesis is right or our alternate hypothesis is right. Okay. So as here we are just testing the mean of the population. We are checking whether the mean of sample and population are same. Okay, so we use this Z score to calculate the test statistics. So this value will be x bar minus mu upon sigma divided by root n. So mu is given to be 600, sigma is wait a minute. So this is sigma, not sigma square, this is sigma. Sigma is 100 and n is 20. We have data for 20 girls. So when we calculate the average of this sample, it came out to be, this sample will came out to be 641. So now we will put these values in this formula and calculate this Z0 value. So this is 641 minus mu naught is 600, sigma is 100 divided by root 20. This value comes out to be 1.8336. Okay. Now this is a one tail test. So the distribution of Z will look like something like this. Okay. Now this, we need to calculate Z alpha, Z.05, which will decide our critical region. So when we when we identify this value from the Z table, when we see it for alpha 0.05, this value comes out to be 1.645. So this Z alpha is 1.645. So this is our critical region. If our Z0 lies in this area, then we need to reject our null hypothesis. And as we can see, this Z0, this is X. This Z0 is somewhere here, 1.8336. This is the Z0. So this Z0 is higher than Z alpha. So this lies in this critical region. So we reject our null hypothesis. Okay. So we reject H0. So in the question we need to test the hypothesis whether H0 is correct or H1 is correct. So we saw that this Z0 value is higher than Z alpha. That's why we reject the H0. So we will claim that this mu is higher than 600. Okay. How to select the distribution generally? No, this is for Z distribution. I didn't understand what you are asking. So this Z0 we are calculating, this Z follows a normal distribution from 0 to 1, right?
So we have different distributions like Z, T, etc., right?
Yeah. So that will, okay. So I will explain that.
Yeah. Not for this question generally. Is there any easy method to identify which distribution has to be used?
Okay. So when this sigma, this is population variance. When this is given, we will use Z0 as our test statistics, which is Z0 is x bar minus mu upon sigma root n. Here we are using this sigma, okay. But when this sigma is unknown, then we use T as T distribution and T as a test statistics, where this T0 will be x bar minus mu upon S by root n. Here we are using S, that's why we are using T distribution, and here this sigma is given, then we will use Z distribution. Okay.
Okay, fine. One more question. How to select the right-tailed or the left-tailed?
Yeah. Okay. So see, when we have our null hypothesis like this, then we will use two-tail test, right? Is this clear?
When the value of mu1 is equal to mu2,
and this alternative hypothesis is that it is not mu1 is not equal to mu2.
okay, fine.
When we have this null hypothesis and this alternate hypothesis, we will use two-tail test. Okay.
Okay.
But when we have this null hypothesis as something like mu1 greater than mu2 or mu1 less than mu2, then we use one-tail test. Okay, because here
Okay.
we are only worry whether mu1 is greater than mu2, okay, or whether it is less than mu2. But here we are just looking whether they are equal or not. So there may be the case that mu1 can be greater than mu2 or mu1 is less than mu2. So that's why for checking both these cases we use this two-tail test. But here we need to verify only one statement, whether that is greater than or equal to, or it is less than. So that's why we will use here one-tail test. Okay.
Okay. Okay.
And then just a minute. Here also, if we have this if our alternate hypothesis is something like this, greater than, then we will, if this z0 is greater than this z alpha, then we reject our null hypothesis. But when the alternate hypothesis is this less than equal to, then we will reject our null hypothesis when this z0 is less than z alpha, not z alpha minus z alpha. So these things also you need to keep in mind. Okay. So moving to the second question. So test at the alpha equal to 0.05 significance level whether the mean of a random sample of size n, which is 16, is statistically significantly less than 10 if the distribution from which the sample has taken has a normal distribution with mean 8.4 and variance 10.24. So what should be the null and alternated hypothesis for this test? Okay, so you are given this problem. So can any one of you tell me what will be the null hypothesis and what will be the alternative hypothesis for this question?
Mu is less than 10. That is the null hypothesis.
No. Actually, here we want to test whether this is less than or equal to 10, right? Whether it is less than 10, significantly less than 10. So,
okay.
So generally what we want to test is our alternate hypothesis. And okay, so this will be h1. Mu is less than 10 will be h1 and h0 will be mu is greater than equal to 10.
Okay.
Okay, so what we want to test will always be the alternate hypothesis. Okay.
Okay.
So this second question, this h0 will be mu greater than equal to 10, h1 will be mu less than 10. Now we are given this x, mu is equal to 8.4, sigma square is equal to 10.24, and we need to check whether this sample mean is less than 10. Okay, so that's why we will, to calculate our test statistics, we will take x bar equal to 10. Then we will write our test hypothesis, which will be x bar minus mu upon sigma by root n. Okay, so this will be 10 minus 8.4. This sigma will be 3.2, and n is given as 16. So divided by 3.2 divided by 4. This comes out to be minus 2. Okay. Now we will see the z 0.05. What is the value of z for 0.05 alpha? So this from z table comes out to be 1.645. Okay. Here our alternate hypothesis is mu less than 10. That's why when our z0 is less than minus z alpha, we reject our null hypothesis. So z0 is minus 2, z alpha is 1.645. So z minus z alpha will be minus 1.645. So this z0 is less than minus z alpha, right? So we reject null hypothesis. Okay.
Can you show me the question once again?
Yeah. Here is the question.
Okay.
So moving to the next question. So now, okay. Suppose it is known from experience that the standard deviation of the weight of 10-ounce packages of cookies is 0.2 ounce. To check whether the true average is 10 ounces on a given day, employees select a random sample of 36 packages and find that their mean weight is 9.45. Now we need to perform a two-tailed Z test on this data, checking at alpha equal to 0.01 significance level. So here this
Can you show me the question once again?
yeah. So here in the question it is told that we need to perform a two-tailed test. That means the alternate hypothesis will be x bar not equals to sample mu, population mu. मतलब x bar is not equal to mu. This will be our alternative hypothesis, and null hypothesis will be mu is equal to x bar. So as given, two-tailed test, this means that our alternate hypothesis will be mu1 that sample mean is not equal to population mean. The sample mean which is x bar, is 9.45. Population mean, which is mu, is 10. Sigma of population is 0.2. N is given 36. Okay, and our null hypothesis will be this x bar is equal to mu, and h1 is x bar is not equal to mu. Now we will calculate our z test statistics. Z naught, which will be x bar minus mu upon sigma root n. So on putting these values, we will get, this comes out to be minus 16.5. Okay, now for two-tailed test, our z distribution looks something like this.
Show me the value once again.
Yeah,
Minus 116.5.
yeah.
Okay, fine.
So this is the x value, this is z. So we need to calculate, this is a two-tailed test, so we need to calculate z alpha by 2 value. So this z alpha is given 0.0, I need to check, it's given 0.01. Okay, I think there is some mistake. This is not 0.01, this is 0.1. Alpha is 0.1, that's why this alpha by 2 is 0.05. Okay, so this z 0.05 will be 1.645. So this value will be 1.645. This value will be minus 1.645. So the critical region is this one and this one. So if our z naught lies either in this area or this, we will reject our null hypothesis. So z naught came out to be minus 16.5, which will be somewhere here, minus 16.5. So this is coming in a critical region, that's why we reject the null hypothesis, as z naught is less than minus z alpha by 2. Okay, moving to the next question. So it is assumed that mean blood pressure, systolic blood pressure is 120 mmHg, and in Honolulu heart study, a sample of 100 people had an average blood pressure level of 130.1 mmHg with a standard deviation is 21.21. So is the group significantly different from the regular population? Okay, so now in this question, what is different? How this question is different from the previous question? The mu is given, the sample size is given, sample average is given, sample deviation, the standard deviation is given. What is different about this question? Here we are given the standard deviation for sample. Standard deviation is not related to the population. That's why in this question we do not, the sigma is unknown. this population standard deviation is unknown. But we know sample standard distribution, sample standard deviation. So that's why we will use t distribution. For testing our hypothesis. So here this H naught is claiming that this x bar is equal to mu, and H1 is saying that x bar is not equal to mu. Okay, so this here this sample of n people had an average systolic blood pressure of 130.1. So x bar is 130.1, and this it is assumed that mean systolic pressure is mu equal to 120, and mu is 120. So this x bar is 130.1, mu is 120. This sample, standard deviation for sample is 21.21. Sample size is 100. Now we will calculate our t statistics, which is x bar minus mu upon s divided by root n. This value comes out to be 4.762. Now, as this is a two-tailed test, we reject null hypothesis if t naught is greater than t alpha by 2 comma n minus 1, or it is less than minus t alpha by 2 comma n minus 1. N minus 1 is the degree of freedom. So in t table there will be two things. One is alpha value and another is this degree of freedom. So degree of freedom is n minus 1, where n is the sample size. Okay, this n is 100. So we calculated t naught. Now we will calculate this t alpha by 2 n minus 1 value, which is nothing but this alpha is given 0.05. So this alpha by 2 will be 0.025, n is 100, so n minus 1 will be 99. So from the t table we will calculate this value t 0.025 comma 99. This comes out to be 1.9842. So our t value, this t naught, which was 4.762. So this t naught is greater than this t alpha by 2 comma n minus 1. So here we saw if this t naught is greater than this t alpha by 2 comma n minus 1, we reject h naught. So as this is greater than t alpha by 2 comma n minus 1, we reject null hypothesis. Okay, so our conclusion is that this group is significantly different from the regular population. Okay, because we rejected the null hypothesis. Null hypothesis was claiming that both these averages are equal, but we are rejecting our null hypothesis. So this says that this group, this sample which we have taken, is different from the regular population, because regular population has mean 120, but this population has mean 130.1. But this is not because this they have this direct difference of 10 mmHg. Here this variance also plays a role. Okay. So now moving to the next question. now suppose we want to test two populations whose mean are mu x and mu y. Okay, sorry, this is so this null hypothesis is mu x equal to mu y, and alternative hypothesis is that mu x is not equal to mu y. And we have this following data that n is equal to 10, x bar is given which is 824.9, variance for x population is given, that is 40. Then this m is given, m is the sample size for population y. Average of y is given which is 818.6. Sigma variance of y is given which is 50. And we are taking this assumption that variance of this population are same. Variance of the population of x and y are same, and these are the samples. These are the sample standard deviations. Okay. So we have two population, x and y. We took a sample of n equal to 10 people from x, and we took a sample of m equal to 10. Okay, so these are two different population, x and y. We took a sample of 10 people from x and 10 people from y. We observed the mean and variance of sample, and from here we observe the mean and variance of sample. So this mean is mu x is 824.9, mu y is 818.6. This sigma square x is 40, this sigma square y is 50. Okay, now we want to test whether this mu x is significantly different from mu y. Okay, this is we need to test. We need to test whether these population mean are significantly different. Okay, and here there is one thing that we need to notice is the variances are somehow known. Okay, the variance of the population are somehow known. Here we are given the samples variance, but the population variance we are assuming that they are somehow known. Okay, they are not unknown. So we will have our this z naught value, which will be mu x minus mu y divided by sigma x square by n1 plus sigma
Not able to see the screen.
okay. Z naught will be mu x minus mu y divided by sigma x square by n1 plus sigma y square by m. Okay, wait. So again, sorry, there is some difference. So here this term is the variances are somehow equal, the population variance. Okay, so and these are given as sample variance, right? These are sample variance. Just a minute. Okay. Okay, so I was wrong earlier. This sigma square y x sigma square y, these are population variance. These are not sample, because for sample variance we use the notation s, small s, but here we are given sigma. Sigma is associated with population variance or population standard deviation. Okay, that's why here in this is sigma x square x and sigma square y. Therefore these are population variance. So when we knows the population variance, our z naught, this test statistics will be mu x minus mu y divided by sigma x square by n and plus sigma y square by m. So this is easy to compute as we know all these values. So this comes out, this is 824.9 minus 818.6 divided by 40 by 10 plus 50 by 10 whole root. This comes out to be 2.1. Alpha is given 0.05. So we will calculate this z naught value, this z alpha by 2, as this is not equal to, that's why it is a two-tailed test. Therefore we are using this z alpha by 2. So this value comes out, this z 0.025, this comes out to be 1.96. Okay, so we reject h naught if our z naught is greater than z alpha by 2, or this z naught is less than minus z alpha by 2. So we are seeing whether this is minus 1.96 and this is 1.96. So we want to see where our z0 lies. So our z0 lies here, 2.1. So this is in rejection region, in critical region. This is the critical region and our z0 lies in this region. That's why we reject H0. Okay. So we reject our H0. Now moving to the next question. Let catalyst X is currently used by a certain chemical process. If catalyst Y gives higher mean yield, we will use it instead. Thus, we want to test whether mu x is greater than mu y or mu x is less than mu y. So here also you can see we want to test whether this catalyst Y gives higher mean yield. That's why this claim is written in alternate hypothesis. In H1 we have written this mu y is greater than mu x, and in null hypothesis we have written mu x is greater than equal to mu y. Okay. Now we here this n is this sample size for both the population are given, mean for both the population are given, and sample variance are given. This time we are given the sample variance. So here the whole picture will change. We won't use the z distribution, we will use the t distribution for calculating our test statistics. So when this is the case, which question is the sixth? So for testing mean of two different population, when population variance are unknown. So when we want to test mean of two different population, when this population variance are unknown and sample variance are known, and sample variance are known, we use the following method. So first we will calculate the T naught, which is mu x minus mu y divided by SP into 1 upon n plus 1 upon m. So we know this mu x value, mu y value, n and m, but we don't know SP. This SP is n1 minus 1 x square plus m minus 1 sy square divided by n1 plus n2 minus 2. Okay. So we know this n is equal to 10, m is equal to 10. This sx square, sy square are given, which is this is 3.89, this is 4.02. So we will calculate this SP, which is n minus 1, which is 9 into 3.89 plus m minus 1 is m is 10, so m minus 1 is 9 into sy is 4.02 divided by n1 plus n2, which is 10 plus 10 minus 2, 18. So this comes out to be 3.958. So now we will calculate our test statistics, which is mu x minus mu y divided by SP 1 upon n1 plus 1 upon n plus 1 upon m. This mu x mu y are given. This is 91.73. Mu y is 93.75. SP is 3.958 divided by 1 by 5. 1 by 10 plus 1 by 10 is 1 by 5. So calculating this, you will get this value comes out to be minus 2.03. Okay. Now we will compare it with this t value. Okay. And here in the question we are looking for less than, the alternate hypothesis is less than, so here we are looking for one tail test. Okay, so here this alternate hypothesis is mu1, we are checking, mu x is less than mu y, that's why we need to we reject H0 if our test hypothesis is less than T alpha, because it is a one tail test, because it is only less than equal to, we only need to check one side, so it's a one tail test, that's why this will be alpha, and degree of freedom for this is n1 plus n2 minus 2. So this alpha is 0.05 and n1 plus n2 minus 2 is 18. This value comes out to be 1.761. So this is 1.761.
Whether alpha value is given in that question?
Yeah, it is given.
Okay.
And if it is not given for this question, you take this alpha. If alpha is not given, you can take it as 0.05.
Okay.
Okay, you need to mention that we are taking alpha equal to 0.05.
Okay.
Okay. So this T 0.05 comma 18 is 1.761, and our T naught came out to be minus 2.03. So this T naught is less than T 0.05 comma 18. That's why we reject null hypothesis, which means that our alternate hypothesis was correct, that sigma y is greater than mu y is greater than mu x. Okay, so I hope you understand this question.
Yeah.
Okay, moving to the next question. So let's test the null hypothesis is mu x equal to mu y, and alternate hypothesis is mu x is not equal to mu y, and this alpha this time is 0.1. Suppose we have this data for n equal to 15, x equal to 24.2, sample the sample variance for x is 10. This m is equal to 10, which is the sample from the population y, sample size from population y is m, y sigma, this average value is 23.9, sample variance for population y is 20. Okay, and this is assumed that these samples are not very close, this sample variance, so we assume that this sigma square x is not equal to sigma square y. Now this will again changes few things. Okay, in the previous question in this question we took this sample variances, but we assumed that it is not given, but we assumed that these population variance are somehow equal for both x and y. But in this question it is assumed that these are not equal. So when it is not equal, we use different method for our hypothesis, okay, for testing our hypothesis. So in this we are we have two population x and y. So this has a sample size of, we took a sample size of 15 from here. Average of this is 24.2 and sample variance is 10. From population y we took a sample of 10. This mean for population y is 23.9 for y sample, and this sample variance for y is 20. Okay, but in this population variance are different. That's why we will the test hypothesis will be test statistics will be calculated as x bar minus y bar divided by sx square by n plus sy square by m. Okay, so in the previous question we were using sp square. Okay, here we calculated this sp, which is n minus 1 sx square plus m minus 1 sy square upon n1 plus n2 minus 2, and then we used this in calculating our test statistics. But here we are directly using this sx square by n and sy square by m. Okay, so this value comes out to be 0.184. But now for calculating the degree of freedom, so now we have our T naught with us. We need to verify our T alpha comma with some DOF. In the previous case we took DOF as n1 plus n2 minus 2. But in this case this formula will change. This DOF will be sx square by n plus sy square by m whole square divided by sx square by n whole square divided by n minus 1 plus sy square divided by m whole square divided by m minus 1. This is the degree of freedom. This is the formula for degree of freedom, for calculating degree of freedom. This comes out to be around 14.9. So this DOF value will be in integers, in integer terms. So the nearest integer to 14.5 is 15. So we will take the DOF as 15. So we want to calculate for this particular question, the T statistics will be T alpha. Okay, so this is here the alternative hypothesis is not equal to, so this is a two-tailed test. That's why we were looking for alpha by 2 value. So we will be looking at alpha by 2 comma 15. Alpha is given to be 0.1, this alpha by 2 will be 0.05. So this 0.05 comma 15 is 1.753. So in two-tailed test we will check whether it is between minus 0.1753 to 1.753, and our value was 0.184. So it is in between minus 1.753 to 1.753. These were the critical region. But our test statistics is not lying in these region, so we fail to reject null hypothesis. Okay, so we cannot reject our null hypothesis as this T naught is between minus T alpha by 2 comma degree of freedom and T alpha by 2 comma degree of freedom. So our T naught lies between this range. We cannot reject. So we fail to reject null hypothesis. So our conclusion is that these averages, this average of x and average of y are equal. Okay, so in this question there is a small error of not small error, this 24.2 and this is 23.9, but they are significantly equal, which means that this variation in these mean values is because of these samples, because of this random sample. If we increase this sample size, if we take it for for the sample size of 1000, the mean will be almost equal. Okay, so the meaning that these are significantly equal is when we increase the sample size, the mean will converge and become equal. Okay, so now moving to next question. So 9 determination of a specific heat of iron had a standard deviation of, we are given the standard deviation of 9 determination. This is the sample of size 9 and standard deviation of the sample is given 0.0086. Assume that these determination constitutes a random sample from a normal population. Test the null hypothesis that sigma is equal to 0.01 against alternative hypothesis that this sigma is less than 0.01 at the level of significance 0.05. So in this question, we need to verify whether the sigma is equal to 0.01 or it is less than 0.01. This is the alternate hypothesis, this is normal hypothesis. This is standard deviation. Okay, so we don't know any test which will tell about the standard deviation, but we have a test which will talk about the variance of the sample or variance of the population. We know something about this thing, variance, but this sigma and this variance are related as it is the sigma square, variance is sigma square. So we can use this variance test to calculate this claim, and we know for testing the variance of the population we use this chi-square distribution. Okay, so this is related to testing variance. So here we claim that H naught will be that sigma square is equal to 0.0001, right, 0001, it's square, or this is less than 0.001. Okay, so in this we will calculate our this test statistics, which is chi square, which is n minus 1 into sample variance divided by population variance. N is given 9, sample standard deviation is given 0.0086. So from here we can calculate this S square. This sigma is 0.01. From here we can calculate this sigma square. So this chi square will become n minus 1 S square divided by sigma square, which is 8 into 0.0086 square divided by 0.01 square. This comes out to be 5.9168. Okay. Okay. Now H1 is sigma square is less than 0.001. So we reject null hypothesis if our chi square is less than the chi square we calculated from the chi square table, which required this n minus 1 comma 1 minus alpha. Alpha is 0.05. So sigma square n chi square n minus 1 comma 1 minus alpha is chi square n is given 9. So this will be 8 comma 0.975. Am I right? No, it will be 0.995. So this is the chi square table. So our alpha was 0.995. This is 0.99 and degree of freedom was 8. So this value is this corresponding value to df8 and this alpha 0.99 is 1.646. So this value is 1.646. We calculated this test statistics, which came out to be 5.9168. So we reject this H0 if this test statistics is less than this value, this chi value which we calculated from the table. But this Z0, this psi naught is 5.9168. This is greater than this value. That's why we fail to reject null hypothesis. Okay. We reject our null hypothesis if this value is less than this value. But as this psi naught is 5.9168, it is greater than 1.646. That's why we fail to reject the null hypothesis and we conclude that this alternative hypothesis is true, which which is saying that this same population standard deviation is significantly less than 0.01. I hope you understand the question. So if you guys have any doubt, you can ask me. So let's move to the next question. So let S1 and S2 are given be the standard deviation of independent sample size N1 and N2. Assume the two population are approximately normal with some variance sigma 1,2 and sigma 2,2 respectively. Then what will be the upper bound for 95% confidence interval for sigma 1 by sigma 2? So in this question we are asked about the upper bound. Okay, so for testing variance of two different population, we use F distribution test.
A screen is not visible.
Okay. So for testing this variance of two different population, we uses F distribution test. So in this we calculate some F, which is, we will find this F naught, which is Sx square upon Sy square. This is sample variance of one sample divided by variance of second sample. Now this value of and this alpha comma n1 minus 1 n2 minus 1. So the corresponding value to evaluate the critical region is F alpha n1 minus 1 n2 minus 1. So in our question this alpha is given to be 0.05. N1 is 16, N2 is 11, S1 is 3.07, S2 is 0.8. In the question it is asked to find the upper bound 95% confidence interval upper bound for the sigma 1 by sigma 2. So in this test we calculate whether we are claiming whether this sigma x square is equal to sigma y square. This will be the H naught. Okay, I will move to the next. So when we claim this, that these two are equal and another that these two are not equal, we calculate a test statistics which is equal to sigma x square by sy square by sx square by sy square, and compare it with this alpha by 2 n1 minus 1 n2 minus 1. As it is not equal to, we use this two-tailed test where we claim this f alpha by 2. Now this f alpha by 2 and this 1 minus alpha by 2 n1 minus 1 comma n2 minus 1. So if this f naught is between f alpha by 2 comma n1 minus 1 n2 minus 1 and f alpha by 2 n1 minus 1 n2 minus 1, and this here it is f1 minus alpha by 2.
Screen is not visible.
So it is visible, right?
Yeah, it's visible now.
So we want to calculate this upper bound, right? Okay. Wait a minute. Huh. So we reject h naught if this f naught is 1 minus alpha by 2 n1 minus 1 n2 minus 1 and f alpha by 2 n1 minus 1 n2 minus 1. If this is something like this f naught is sx square by sy square. Okay, so we can write this sigma x by sigma y is equal to sx by sy into f alpha by 2 n1 minus 1 and n2 minus 1, or we can write this sigma x by sigma y sx by sy into 1 upon f alpha by 2 n1 minus 1 n2 minus 1. This is root. So how we came to this conclusion? Because here we are claiming that if this value, this f naught is between this, then these both sigma x and sigma y are equal. Okay, they are equal. If f naught lies between this, then sigma x square is equal to sigma y square, which means sigma x is equal to sigma y. Okay, so what we are doing here is to find the upper bound for this interval distribution. We will take our this let's take this thing. So to calculate this confidence interval, we will multiply our test statistic value with our test statistics, and that will be the range, this confidence interval for our claim. Okay, so to find this so for testing the variance, we will test the this thing, this, what is this proportion, okay, by using this sample variance and using this test hypothesis. If this so here we are just multiplying it with the test hypothesis to get our range, to get the confidence interval. So this, by this we will get the upper bound, and by this we will get the lower bound. This is when we are divided it by this test statistic value, and when we are multiplying it with the test statistic value. So in the question we are given these values. This sx square is 3.07 square, sy square is 0.8 square, this n1 is 16, n2 is 10. So this sigma x square by sigma y square, upper bound, for upper bound, this value will be sx square by sy square into f alpha by 2 n1 minus 1 comma n2 minus 1. This is 3.07 square divided by 0.8 square into f 0.025, as alpha is 0.05, comma n1 minus 1 is 15, n2 minus 1 is 10. So when we look at the f table, we have two degree of freedoms. So here it is one is 15 and another is 10. So now for sigma x by y, this will be sx by sy into root f alpha, this f 0.025 comma 15 comma 10. This is 3.07 divided by 0.8 into, this value comes out to be 3.5546 from the table. So when we calculate this value comes out to be 7.235. This will be the upper bound. This will be the upper bound for sigma x by sigma y. Similarly, lower bound for sigma x by sigma y is sx by sy into 1 upon root 3.5546, which will come out to be around, just you need to calculate this value. So this will be the lower bound. For lower bound we are dividing it by this value, and for upper bound we are multiplying it with this value. But here we are putting these sx by sy, and here also sx by sy. If you switch these things for upper and lower bound, then the answer will come same. So you need to fix this ratio, sx by sy. Here also it is sx by xy. For upper bound you will multiply it with this f statistic, and for lower bound you need to divide it with this f statistic. Okay, moving to the next question. So now we will see uh, how to test whether the certain data is following a particular distribution. Okay, so this employers want to know which days of week employees are absent in a 5-day work week. So most employers would like to believe that employees are absent equally during the week. So they will say that on all the days there are equal number of absent people. Now let's suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. So the results are shown in the table below. So for the population of employees, do the days for the highest number of absences occur with the equal frequencies during a 5-day work week? Test at a 5% significance level. Okay, so this is the number of absent people on Monday, Tuesday, Wednesday, Thursday and Friday. Here we want to check whether this number of absent, the highest number of absent people are equal throughout the week. Okay, in the data you can see they are not equal. Okay, in this random sample you can see that this is not equal, but we are asked whether those are equal based on this given data. So if those are equal, then what should be that equal number? So the total number of absent people are 60. Here we are, this suppose a random sample of 60 managers were asked. Okay, so this 60 divided by 5 is 12. So for Monday, Tuesday, Wednesday, Thursday, Friday, data is given something like this. 15 people are absent on Monday, 12 are on Wednesday, 9 on Wednesday, 9 on Thursday and 15 on Friday. This is 60 total, I guess. 15 plus 30. What is this number? This is 60. So we want to check whether the number of absences are equal throughout 5 days. So if it will be equal, what will be the maximum number of absent people per day? So total absent people in a week are 60. Total number of absent people in 5 days is 60. So total number of absent people in one day will be 60 by 5, which is 12. So here the expected number of absent people is 12. We are given this is the observed data. This is the observed data. So if this absent people are 12, then we are saying that expected number of absent people is 12. Okay, so here we want to see this claim whether this number is 12. So here we will use this distribution test where we calculate this chi-square corresponding to our test statistic, which is d0 square, which is nothing but OI minus EI whole square divided by E. EI. Okay, so this observed data is OI is 15, 12, 9, 9, 15. Expected EIs are 12, 12, 12, 12, 12. So D naught square will be 15 minus 12 whole square divided by 12. This is for first term. For second it will be 12 minus 12, which will be 0. 12 minus 12 whole square divided by 12. Because we need to divide it by EI. EI is same for all the i's. That's why we are dividing by 12. For third term we will be doing 9 minus 12. For fourth also we will be doing 9 minus 12. So 9 minus 12 whole square divided by 12 plus 9 minus 12 whole square divided by 12. And for last term we will be doing 15 minus 12 whole square divided by 12. This value comes out to be 3. Okay. Now we will calculate our chi-square for k minus 1. What is k here? K minus 1 comma alpha. Alpha is the level of significance and k is the number of observation. Okay, number of observation. So there are total 5 observations. So chi-square, we are looking for chi-square for degree of freedom 4 and for alpha 0.05. So this value comes out to be 9.488. And our psi naught square from the test statistics came out to be 3. So as this is less than this value, we fail to reject null hypothesis. So sorry, this is not x naught, this is d naught. I will rewrite it again. So this d naught square we calculated here, it came out to be 3. This we calculated from chi-square table. This came out to be 9.488. So if this d naught square is greater than the chi-square k minus 1 comma alpha, then we reject h naught. But in our case, this d naught, this d naught square is less than 4 comma 0.05. That's why we fail to reject h naught. Okay. So here we fail to reject the h naught, which means that if we increase the number of observation, the average number of absent people will be equal throughout the week. Okay, it is not significantly that different. Okay. Moving to the next question. This is the This is the question based on this ANOVA technique, where we are calculating the variance within the data and between the data. We need to verify whether the difference between the population is because of the variances of the population, or this is not, this is just the variant, this is just the difference based on the sample we collected. Okay, so just read the question and I will go through it. So this ANOVA technique it is a hypothesis regarding the equality of 2 or 3 population means by analyzing their variance. So by analyzing the variance of these 3 food categories, we will tell whether these 3 population are same or different. Okay, it allows us to determine whether the difference between the samples are simply due to the random error or due to the symmetric treatment effects that causes the mean in one group to differ from the mean in the another, which means that we will calculate the, let's say we will calculate the mean values for every sample, and these mean values are different. So one thing that these are different is because of the different variance among these population, and another reason is that there can be a random error in collecting the sample. Okay, so the difference is because of that random error. So in that case the variance won't have much to contribute in the differences of the mean. The variances can be almost equal, but still the means are different. That is because of the random error. So here we will calculate whether the difference in the mean weights is due to the variances or it is due to the random error. Okay, so here our null hypothesis will be that mean of all these samples are equal, and alternative hypothesis is that like at least one of these pair, either food 1 or food 2, food 2 or food 3, or food 1 or food 3, they have different means. Okay, either one pair will have a different mean. So we will compare the variance of food 1 to food 2, food 2 to food 3, and we also calculate the variance within the group and between the group. Okay, so in such questions the null hypothesis will be that mu1 is equal to mu2 equal to mu3. H1 is any one of the pair has different mean. Okay, so in this question what we will do, first we will calculate the average of each group. Okay, so we calculate x1 bar, x2 bar and x3 bar. So from this data we will calculate x1 bar, x2 bar, x3 bar. So this values comes out to be 10.66, x2 bar comes out to be 5.83, and x3 bar comes out to be 9.67. Now we will calculate the x bar, which is xg bar, which is average of whole sample, which means we will calculate the mean for all these values. Okay, for all these values. So that value comes out to be 8.56. I am taking it as x bar. Now what we will do, we will calculate the sum of squares between groups. This is nothing but, we denote it as by SSB, which is n into xi bar minus x bar whole square. So here what we are doing, we are calculating the difference between the average of each group with the whole sample average. This is the average for whole data, this is the group data. So we are trying to identify the variance between the group mean with the whole mean. Okay, and here is the number of observed values. So in this ANOVA question, these n values are same. This n is 6 for every category. So this will be same. So this n is 6. So this SSB value for our data will be 6 into summation of xi bar minus x bar whole square for I equal to 1 to 3. So x1 bar minus x bar square plus x2 bar minus x bar square plus x3 bar minus x bar square. We know these x1 bar, x2 bar, x3 bar values and x bar values. We put these values in the equation and we get this SSB value as 77.74. Okay. Now we calculate this sum of squares within the group. This is within the group. So these xij values are for group I. We will go through all the values and see their difference with the group mean. So here this is group 1. Now this x11 will be for group 1 the first value, x21 will be 12, x31 will be 19, x41 will be 8, and so on. So now we will check the difference of each element of group with the group mean. Okay, this is the group mean and these are the value of all the elements of the group. Okay, and we sum it over all the groups for all the values. This is the sum of squares within the group and it is denoted by SSW. So this will be, so for these I will be from 1 to 3 and J will be from 1 to 6. So this will be, first is 8 minus 10.66 whole square, or I can write it as this: x11 minus x1 bar square plus
Screen is not visible.
x21 minus x1 bar square, x31 minus x1 bar square plus up to x61 minus x1 bar square. Then we will add x12 minus x2 bar square. We started for group 2. We will go up to x62 minus x2 bar whole square. Then we move to group 3, which will be 13 minus x3 bar whole square plus x63 minus x3 bar whole square. So these food 1, food 2, food 3, 8, 12, 19, 8, 6, 11. For food 2 it will be 4, 5, 4, 6, 9, 7. 11, 7. Okay, these are the values. So now what is SSW? The mean is 10.66 for this group 1. We will subtract this value, square it, and then add it with this next value. Similarly, for this second group, the average is 5.833. We will add this to these value, and we do it for all the elements of this group. And then we go to this third group. Average of this third group is 9.67, and we do the same. So we add all these values, and this all values is SSW. Okay, this SSW comes out to be 156.4915. After doing this, we will calculate mean sum of squares between the group and mean sum of square within the group. This will be SSB divided by DF1. This will be SSW divided by DF2. Here this DF1 is K minus 1. K is number of groups. Okay, pay attention, it is number of groups. DF2 is N minus K. This is total observation, and K is number of groups. So in the question there are 3 groups. Okay, there are 3 groups: food 1, food 2, food 3. So this K is equal to 3. The N is, capital N is total observation. So total observations are there are 6 in each group. Okay, there are 6 in each group, so 6 into 3, 18. This n is equal to 18. So df1 is k minus 1, which is 2. df2 is n minus k, which is 18 minus 3, which is 15. So we calculate this mean SSB, which is SSB divided by df1, which is 7.74 divided by 2, which is 38.87. Then we calculate mean SSW, which is SSW divided by df2, which is 156.4915 divided by 15. This value comes out to be 10.4328. After this, we will calculate the F value, which is our test statistics. This is nothing but mean sum of square between the groups upon mean sum of square within the group. This is we calculated. This is 38.87. This is 10.4328. This value comes out to be 3.7257. Now we will calculate the F distribution value, which is F n minus 1, sorry, F k minus 1 n minus k comma alpha. So this is 2 comma 15 comma 0.05. So this, when we calculate it from the F distribution table, this value comes out to be 3.6823. So in the ANOVA, we will just a minute. So if this F value is greater than this F k minus 1 n minus k comma alpha, then we reject H naught. So as this value F is 3.7257 and F k minus 1 n minus k alpha, this is 3.6823. This means that this holds, this F is greater than this value. That's why we reject the null hypothesis, which means that these different population has different mean. They do not have equal mean, they have significantly different means. Okay, because we considered that H naught, that all these mu's are equal for all the different population, but we rejected our null hypothesis, which means that H1 is significantly correct, which is any one of the pair has different means. Okay, so this is a quite lengthy process, because first we need to calculate the sum of squares between the group, then we need to calculate sum of square within the group. Okay, then we need to calculate mean sum of square between the group, mean sum of square within the group. We need to calculate these df1, df2. Then we need to calculate the F value. No, first we will calculate this mean SSB, mean SSW. Then we will calculate this F value and compare it with this F distribution value. If this is greater than this value, this table value, then we reject our null hypothesis. So today I am going to discuss these many questions. So if you guys have any doubt, you can ask in the next session. So in this test hypothesis, there are two things, like there are few things that you need to keep in mind. First is whether it is a two-tail or one-tail test. It is a one-tail test when the alternative hypothesis has this greater than or greater than or less than sign. If the alternate hypothesis has not equal to sign, then it is a two-tailed test. Second thing is, you need to see whether in the question there is a sample standard deviation, sample variance is given, or the population variance is given, because based on this test statistics will change. If we know the population variance, then we use Z distribution, but if we do not know this population variance, we need to use T distribution for our testing purpose. Okay, and this is for the when we are testing for the mean, but when we are testing for the variances, we use the F distribution. Okay, and if we need to check whether the distribution is following a particular distribution, then we will use the chi-square table, the chi-square test. Okay, so for different tests we use different distributions, and within the same frame of questions where we are analyzing the mean of the samples, we use either Z or T test depending on the variance of the population is given or whether the variance of sample is given. So these are 2-3 things that you need to keep in mind while doing these kind of questions, because these are very lengthy questions, and if you made these small mistakes, then there is no point of solving the whole question. So you need to see whether you are given the sample variance or the population variance. So you need to understand why we are using this test hypothesis. We are using it because we want to relate the sample statistics with the population statistics, and these tests are giving us the result whether these samples are related to the population or not. Okay, so I am going to end this session now, and if you guys have any doubt, you can ask in the next question, in the next session. So, okay, thank you, bye.